Welcome to the first lecture of the fifth week of Lent term. And when we finished last time's lecture, we were discussing the fundamental theorem of arithmetic, which says that every non-zero integer can be written as a product of primes, essentially in a unique way. And last time we established the existence part, and the plan is to start today's lecture by also showing the uniqueness part. So let's recall the precise statement of the fundamental theorem of arithmetic. It says that every integer n which is not equal to 0 can be written as a product n is equal to c times p1 to pk, where this c is equal to plus 1 or minus 1, and that takes care of the sign of this n. So if n is positive, then c is plus 1. If n is negative, then c is minus 1. And p1 to pk, they are all primes. And of course, all these primes are strictly bigger than 1. So if n is equal to plus or minus 1, no primes can appear, and in that case this empty product, when there are no primes at all, is taken to be equal to 1. So last time we proved the existence part, but today the plan is to prove the uniqueness part. So that says that moreover this expression is unique except for the ordering of the primes. So the same primes appear the same number of times, but all that can change is the order of the primes. So you can permute these primes amongst each other, but the same primes will appear the same number of times. So that uniqueness part we will prove today. So besides that, we will also discuss the greatest common divisor computation. So far we have seen Euclid's algorithm for calculating the greatest common divisor of two numbers, and that was based on this repeated division with remainder. But now we will see that if the two given numbers are such that we also know their prime factorization, then we can use this prime factorization to also compute the GCD. So we'll prove that result too. And then we will begin the discussion of modular arithmetic. So that topic will be finished next time, but we will start the discussion of that today. Okay, but the first task at hand is to prove the uniqueness part of this fundamental theorem of arithmetic. So let us now prove the uniqueness part of the fundamental theorem of arithmetic. Now to do this, we will consider the following set S, which is the collection of all non-zero integers n such that n does not have a unique factorization into primes. And of course our aim is to show that S is the empty set. So let us suppose that S is not the empty set, and we will arrive at a contradiction. So we are assuming that S is not the empty set, and let us now first show that S has positive integer members. In the case when S has a negative integer member, let us show that minus of that also belongs to the set. So let us suppose that M is a member of S such that M is strictly less than 0, and then we will show that minus M also belongs to the set. Now what does it mean that M belongs to S? It means that it has two different factorizations into primes. Let one factorization be C times P1 to Pk, and the other factorization be C prime times Q1 to QL. Now we know that M is negative. Okay. Meanwhile, this part P1 to Pk, that is positive. So it has got to be the case that C is negative, but C is plus or minus 1, so C is minus 1. And the same argument shows that since M is negative and Q1 to QL, that part is positive, we must have that C prime is minus 1. So you have got that C and C prime are both equal to minus 1. And so by multiplying throughout this equation by minus 1, you get that minus M is equal to P1 to Pk, and that's equal to Q1 to QL. Now, if this is the empty product, this would be 1. Okay, but then this cannot be the empty product because these are supposed to be different, and we already know that C is equal to C prime, so the only difference must be amongst these. So if this is 1, then this cannot be 1, but then you cannot have this equality, right? And so it cannot be the case that this is equal to 1. So this is actually a product of primes, and then this will also be a product of primes. So you have got two different products of primes, and that is both equal to this minus M, and so this integer minus M has two different factorizations into primes, so it belongs to S. But since M was assumed to be negative, this minus M is positive. Okay, so whenever you have a member of S which is negative, minus of that will also belong to the set and it will be positive. So surely this S contains positive members too. So if I look at S plus, which is the set of all members of S which are positive, then this is a non-empty set. Okay, and moreover, since it's just a collection of positive members, it's a subset of the set of natural numbers, and so you have a non-empty subset, this S plus, of the set of natural numbers, and so by the well ordering principle it has a least element. So the minimum of S plus, which we call n star, exists. Okay, so this n star being the minimum of S plus certainly belongs to S plus, and so this n star will have two factorizations. Let one factorization be C times P1 to Pk and the other factorization be C prime times Q1 to Ql. Now n star, since it belongs to S, is positive, right? So this is positive, and since this part is also positive, it must be that C must be positive, but C is either plus 1 or minus 1, so C has to be plus 1. And the same argument shows that also C prime must be plus 1. So since C and C prime are both equal to plus 1, what we have got is P1 to Pk is equal to Q1 to Ql, and these are different. So if this is 1, then this can't be 1, but then it will have to be bigger than 1, and then you can't have this equality. So this can't be 1. So this is actually a product of primes, and so is this. So if I look at P1, if I separate out P1, then P1 times whatever is the rest, which is an integer, is equal to this one. So P1 divides this. But P1 is a prime, and so we know that whenever a prime divides a product of numbers, it has to divide at least one of them. So we know that P1 divides some Qi. But we know that Qi is a prime too. So the only factors it has which are positive are 1 and Qi itself. But P1 is not equal to 1 because being a prime, it is strictly bigger than 1. So it has to be the case that this factor P1 of Qi, since it's not equal to 1, has to be Qi. So P1 is equal to Qi. So if I cancel P1 against the Qi over here in this equality, what I'm left with is P2 times so on up till Pk is equal to this stuff with the Qi removed. So that is Q1 to Qi minus 1 and then Qi plus 1 all the way up till Ql. Now these two are equal, and whatever integer this is, which is a positive integer, we call that as n prime. Now let us first note that this n prime has two different factorizations. So I am claiming that this factorization is different from this one. Why is that so? Well, we knew that this factorization is different from this factorization, and since C and C prime are the same, both equal to plus 1, it must be that this is different from this one. But we also knew that P1 is equal to Qi. Okay, so it must be that the rest of this stuff is equal to the stuff over here with the Qi removed, which is exactly this, P2 to Pk, and this thing with the Qi removed is exactly this. So these two factorizations must be different. So you have got this n prime is an integer which is non-zero, and it has two different factorizations. Okay, moreover it's positive also, so it belongs to this S plus. And now let us show that this n prime is actually strictly less than this n star. Okay, that's because 1 is strictly less than P1 because P1 is a prime, and so if I multiply both sides of that inequality by this boxed integer which is P2 to Pk, then the inequality is preserved because this is a positive number. But P1 times P2 to Pk is exactly what n star was because this C was plus 1, right? So this is just n star. On the other hand, P2 to Pk is what I'm calling n prime. So I've got that n prime is strictly less than n star, okay? But it belongs to S plus, but this n star was supposed to be the least element, but here is an element which I've found which is even smaller than n star. So that's a contradiction, and this contradiction shows that our original assumption that this S is not empty cannot be true. And so the set of integers which are non-zero and which do not have a unique factorization is empty, and so every non-zero integer has a unique factorization. So this completes the proof of the uniqueness part of the fundamental theorem of arithmetic. Alright, so let's look at some examples of prime factorizations. Now the way to compute the prime factorization of a given non-zero integer is to keep extracting prime factors. So for example, if the integer was 36, we see that it's clearly divisible by 2. So you can write it as 2 times 18. 18 is further divisible by 2, that's 2 times 9, and this 9 can be written as 3 times 3. And now we can't go any further because each of these is a prime number, and so we have got our prime factorization. You can write this more succinctly as 2 to the power 2 times 3 to the power 2, so as powers of primes. And if the integer were 224, then let's do a similar process. It's clearly divisible by 2. It's 2 times 112. This is further divisible by 2. And then 56 is further divisible by 2. And this 28 is further divisible by 2. And you get 2 times 14. And this 14 can be written as 2 times 7. So this is the prime factorization because each of these factors is a prime number. And we can write it succinctly as 2 to the power 5 times 7. Now, the missing primes you can always introduce by raising the missing prime to the power 0 because that's just 1, and so you can also write this like this. It's 2 to the power 5 and the prime after 2 is 3, so since that's missing over here we write it as 3 to the power 0. Then the next prime is 5, which we write as 5 to the power 0. Since it's missing over here, 5 to the power 0 is 1, and 7 is present, so then you have 7 to the power 1. Now earlier we had seen how to compute the GCD using Euclid's algorithm, but now let's see, knowing the prime factorization of the given integers, how we can calculate the greatest common divisor. So earlier we had done this computation where using the Euclid's algorithm we had found that the greatest common divisor of these two integers 36 and 224 is equal to 4. But now let us employ the prime factorization which we have just found to find the greatest common divisor of these two. The process is like this, and then we'll justify it. You see that 224 is 2 to the power 5 times 3 to the power 0 times 5 to the power 0 times 7 to the power 1. 36, which we know is 2 to the power 2 times 3 to the power 2, you can write as, with the same primes as listed over here, 2 to the power 2 times 3 to the power 2, well 5 is missing, so we introduce it as 5 to the power 0, which is equal to 1. And then 7 is also missing, which we introduce as 7 to the power 0 because that's equal to 1. So 36 has this prime factorization and 224 has this prime factorization. And notice that you have the same primes appearing, 2, 3, 5, 7, 2, 3, 5, 7. Of course, some of the powers are equal to 0. Then we can just write the GCD by inspection as follows. You write first the same primes which are in these two lists, so 2, 3, 5, 7. And the powers to be used are the minimum of the corresponding powers. So you see that 5 and 2, the smallest is 2, so you write down 2 there. 0 and 2, the smallest is 0, so you write 0 there. 0 and 0, the minimum of these two numbers is 0, so you write 0 there. 7 to the power 0, 7 to the power 1, so if I look at the powers, they are 0 and 1, the minimum is 0, so you write 0 there. And what we have got, well, this is 1, this is 1, this is 1, and 2 to the power 2 is equal to 4. So it seems to work. Okay, let's try one more example. Let's calculate the GCD of 24 and 35. Now in the last lecture we had checked that these two are in fact co-prime, that GCD is equal to 1, and to do this we had used Euclid's algorithm. But now let us use this prime factorization method. What's the method? Well, we first find the prime factorizations for 24 and 35. 24 is divisible by 2, it's 2 times 12. 12 is divisible by 2, it's 2 times 6. 6 is divisible by 2, it's 2 times 3. And now we have got its prime factorization because each of these is a prime number. So it's 2 to the power 3 times 3 to the power 1. Meanwhile, 35 is equal to 5 times 7. Both of these are primes. And so we have got the prime factorization for 35 as well. So the procedure is you write down both of these using the same primes. Okay, so this is 2 to the power 3 times 3 to the power 1. The next prime is 5, which appears here, but it doesn't appear in this factorization. So we put 5 to the power 0, which is equal to 1. And similarly, 7 to the power 0. And likewise 35, the 2 and 3 are missing. So you put 2 to the power 0, 3 to the power 0, 5 to the power 1, 7 to the power 1. So these are the prime factorizations where we have written it in a way so that the same primes appear in both of these. Then the process for writing the GCD is simply by inspection. We just first write down all the primes 2, 3, 5, 7, and what power should appear here? We take the minimum of the corresponding powers. Minimum of 3 and 0 is 0, so 2 to the power 0. Minimum of 1 and 0 is 0, so 3 to the power 0. Minimum of 0 and 1 is 0, so 5 to the power 0, minimum of 0 and 1 is 0, so you have 7 to the power 0. So this is 1, this is 1, this is 1, this is 1, so it's equal to 1 as expected. Okay. So we have a procedure, it seems to work, at least in these two examples, but now we will prove this. Now to justify this new method of calculating the greatest common divisor based on this prime factorization, we will need the following lemma, and this lemma says that if d and n are two natural numbers and d divides n and d has this prime factorization p1 to the power alpha 1 up till pk to the power alpha k, where p1 to pk are primes and they are distinct primes arranged in increasing order, and alpha 1 to alpha k, these powers are non-negative integers. Okay, and of course, so some of them might be 0, and let n have the prime factorization p1 to the power beta 1 all the way up till pk to the power beta k, where again you have that beta 1 to beta k are non-negative integers. Then the conclusion is that alpha 1 is less than or equal to beta 1 all the way down to alpha k is less than or equal to beta k. So if d divides n and d and n have this prime factorization, then the corresponding powers which appear in d, they are less than the corresponding powers which appear in n for the same prime. Okay, so that's the content of this lemma, and let's prove this. So let us first show that alpha 1 is less than or equal to beta 1. So let's suppose on the contrary that alpha 1 is strictly bigger than beta 1, and we'll arrive at a contradiction, and that will show that alpha 1 is less than or equal to beta 1. So let's suppose that alpha 1 is strictly bigger than beta 1. Now what we know is that this d divides n. That means that n is d times some integer q, and in fact since n is positive and d is positive, them being natural numbers, we must have that q must also be positive, so it's some natural number. So you have got n is equal to qd with q a natural number, and n we know has this factorization, so we write that down, and d has this factorization, so we write that down. Now on this side you have p1 appearing beta 1 times, and here you have p1 appearing alpha 1 times, and alpha 1 is strictly bigger than beta 1, so p1 appears more times on this side. So if you cancel all the p1s which appear beta 1 times over here against those p1s which appear over here, there will be some p1s which are still left on this side. And how many are left? Well, alpha 1 minus beta 1. Okay, so by the cancellation law, you get that p2 to the power beta 2 all the way up till pk to the power beta k is q times p1 to the power alpha 1 minus beta 1, then p2 to the power alpha 2 all the way up till pk to the power alpha k. Now let's note that alpha 1 minus beta 1, since alpha 1 is strictly bigger than beta 1, is a positive integer. In other words, it's a natural number. Okay, so this p1 to this natural number power times some integer is equal to this integer. So it follows that p1 to the power alpha 1 minus beta 1 divides this integer. Okay, so this means that p1 repeated alpha 1 minus beta 1 times, and this is a natural number, divides this integer which I have indicated by this box. But that means that p1 divides this, right? So p1 divides p2 to the power beta 2 all the way up till pk to the power beta k. But then we knew that whenever a prime divides a product of numbers, it has to divide at least one of them. So let's suppose that p1 divides pl to the power beta l, but if this beta l is equal to 0, we would get p1 divides pl to the power 0, which is 1, but then p1 would be less than or equal to 1, and we know that p1 is strictly bigger than 1 because it's a prime number. So first of all, this beta l can't be 0. So then you have got that p1 divides pl times pl beta l times, and beta l is now a natural number, but again by this fact it must be then that p1 divides pl. But PL has the only two positive factors 1 or PL, and P1 is not equal to 1 because it's a prime number, so it has got to be equal to PL. But that's a contradiction because all of these primes are distinct, and so P1 is not equal to PL if PL is in this list from 2 to K. So this contradiction shows that alpha 1 is in fact less than or equal to beta 1. And a similar argument can also be used to show that alpha 2 is less than or equal to beta 2 and all the way up till alpha k is less than or equal to beta k. Okay, so that proves this lemma. So we are now ready to prove this theorem, which gives the theoretical justification for the method that we have just learned of computing the greatest common divisor based on prime factorizations. So suppose that a and b are two non-zero integers, and suppose that they have these prime factorizations. So a is equal to c times p1 to the power alpha 1 up till pk to the power alpha k, where these p1 to pk are distinct primes arranged in increasing order, c is plus 1 or minus 1, and these alpha 1 to alpha k are non-negative integers. And similarly b can be written as c prime, which is plus or minus 1, times p1 to the power beta 1 up till pk to the power beta k, where these beta 1 to beta k are non-negative integers. Then the greatest common divisor of a and b can be written down by inspection. You use the same primes p1 to pk, and the powers that you use are the minimum of the corresponding powers which appear in these two factorizations. So p1 to the power the minimum of alpha 1 and beta 1, and similarly pk to the power the minimum of alpha k and beta k. So we want to prove this. Now first of all, since a and b are non-zero integers, we know that the greatest common divisor exists, and let's call it d. Okay. Now d has its own prime factorization, and let's show that in that prime factorization only the same primes can appear, p1 to pk. Okay, indeed, because if p is any prime which divides d, then since this prime divides d and d divides a, it follows that p will divide a. But a has this prime factorization, so it's c times p1 to the power alpha 1 up till pk to the power alpha k. So we have got that this prime p divides this product. Now p cannot divide c, because otherwise the mod of p would be less than or equal to mod of c, which is equal to 1, and p being strictly bigger than 1, we would have that 1 is strictly bigger than 1, which is a contradiction. So p has to divide some pi to the power alpha I. Okay, and again alpha I can't be 0, because again you would get that p divides 1, so that is absurd. So it must be that alpha I is positive, and then p divides pi times pi times pi taken alpha I times. Okay, and then p would have to divide pi. Okay, so since pi has just the factors 1 and pi, and p is not equal to 1, then p would have to be equal to pi. So this prime, any prime which divides d, has to be one of these primes. Okay, and so in the prime factorization of d, the only primes which can appear are these p1 to pk. And since d is positive, the coefficient that appears over here, which is plus or minus 1, is in fact plus 1, and you have p1 to the power gamma 1, pk to the power gamma k for some non-negative integers gamma 1 to gamma k. Now we want to show that these gamma 1 to gamma k which appear here are actually these powers. Okay, so let's first show that gamma I is less than or equal to the minimum of alpha I and beta I, and then we'll also show that gamma I is bigger than or equal to the minimum of alpha I and beta I. Okay, so let's first show these inequalities. Now we know that d divides a, and so by the lemma that we just proved, we know that the powers which appear over here are less than the corresponding powers which appear in a. So we know that gamma 1 is less than or equal to alpha 1, and similarly gamma k over here is less than or equal to alpha k. Similarly, d also divides b, because it's the greatest common divisor, in particular it's common divisor, so it certainly divides b. And so we know that gamma 1 is less than or equal to beta 1 all the way up till gamma k is less than or equal to beta k. So we also have these inequalities. But gamma 1 is less than or equal to alpha 1 and less than or equal to beta 1, so it's less than or equal to the minimum of these two numbers, because the minimum of these two numbers is one of the two, but in both of these cases we have that gamma 1 is smaller. So we have this, and similarly since gamma k is less than or equal to alpha k and also less than or equal to beta k, it's less than or equal to the minimum. So we have all these inequalities. Now we would like to show that also bigger than or equal to holds, and that's what we do next. So we will now show these reverse inequalities, and to do that, let us define d prime to be this number, p1 to the power minimum alpha 1 beta 1 all the way up till pk minimum of alpha k beta k. Now let's observe that d prime divides a. Let's recall that a had this factorization where the powers of p1 to pk which appeared were alpha 1 to alpha k, and now we have corresponding powers which are smaller. So we know that minimum of alpha 1 and beta 1 is certainly less than or equal to alpha 1, and we know that whenever you have pi to a smaller power, that divides pi to the bigger power, right? And so we know that pi to the power minimum of alpha I beta I certainly divides pi to the power alpha I, because this is smaller than this one. So because of that, we know that this one divides this and so on up till this one divides this, and so their product will certainly divide this product. So we know that d prime divides a, and similarly, since each of these is also less than the corresponding beta, so this is, for example, less than or equal to beta 1 and this one is less than or equal to beta k, it also follows that d prime divides b, because in b the powers which appear are beta 1 to beta k. So since this is a common divisor of both a and b, and since d was the greatest common divisor, it follows that d prime has to divide d. So this divides d, which had the factorization p1 to the power gamma 1 up till pk to the power gamma k. But by that lemma that we just proved, we then know that this must be less than or equal to this one, and all the way up till this must be less than or equal to this one. So we also get the reverse inequalities. And together with what we proved over here, what we knew from over here, it now follows that gamma 1 is equal to minimum of alpha 1 beta 1 all the way up till gamma k is equal to minimum of alpha k beta k. And so we have got that d, which is the greatest common divisor of a and b, which is this thing, but now gamma 1 is this and gamma k is this. So we have got this thing. So this completes the proof of this theorem, and this theorem gives justification to our method. We will now show the theorem which says that there are infinitely many primes. Now this is a theorem that you must have seen before, and you must have seen a proof of this also. But let us revisit this theorem, because I want to emphasize that in the proof we use the fundamental theorem of arithmetic, which we have now proved. So here is one proof. Suppose that there are only finitely many primes, and suppose that there are n primes, where n is a natural number, and let the primes be listed as p1 to pn. So these are all distinct primes, and these are the only primes that there are. Let us look at this number capital N, which is the product of these primes plus 1. Okay, so then all of these are positive, we know, and so this is a positive number, it's a natural number, and it's a number which is strictly bigger than 1 because this is positive. So by the fundamental theorem of arithmetic, and here is where we use it, we have a non-zero number and it has a factorization into primes, and the primes must be primes from this list because these are the only primes. So it's the product of some primes pi1 up till pin. Moreover, this cannot be the empty product, it can't be 1, because we know that this capital N is strictly bigger than 1. Okay, so we have such a factorization into primes. Now pi1 multiplied by the rest of this stuff, which is an integer, is equal to this capital N, so pi1 certainly divides this capital N. And let's recall this capital N is equal to p1 to pn plus 1. On the other hand, pi1 certainly divides this product p1 to pn because pi1 arises somewhere in this list. Okay, so pi1 multiplied by the rest of the stuff is equal to this thing, so pi certainly divides this. Now pi1 divides this and pi1 also divides this, so pi1 will divide their difference, but this minus this is just 1. So you have got that pi1 divides 1. But then we know that the size of this must be less than or equal to the size of this non-zero integer. So we must have that mod of pi1 is less than or equal to mod of 1. But mod of 1 is 1, and since pi1 is a prime, it is a positive number, and so the mod is itself, right? And pi1 we know on the other hand is also strictly bigger than 1. So what we have got is that 1 is strictly less than 1, which is a contradiction, and this contradiction arose because we assumed that the number of primes is finite, and so that cannot be true, and so there are infinitely many primes. Okay, so let us take stock of how far we have come in chapter 5. We began chapter 5 with a discussion of the division algorithm. So that was this theorem which told us that any integer can be divided by any non-zero integer. In the process we get a quotient and a remainder, and the remainder is such that it's bigger than or equal to 0 and strictly less than the mod of the integer with which the division is taking place. Then we discussed divisibility, and we also discussed the greatest common divisor and Euclid's algorithm to calculate the greatest common divisor. And then recently we have been discussing prime numbers, and we have just proved the fundamental theorem of arithmetic and also learned how to use prime factorization to calculate the greatest common divisor. Now there is only one more topic left in chapter 5, which is on modular arithmetic and the set Zn together with the operations of addition modulo n and multiplication modulo n. So let us now begin with this topic. So now we'll begin the discussion of the final topic in chapter 5, which is on this modular arithmetic. So let us begin with a definition. Suppose that n is a natural number, then given integers a and b, we say that they are congruent modulo n if n divides a minus b. And in this case, we write this, which is read as a is congruent b mod n. Okay, and that just means that n divides a minus b. Now we note that if n divides a minus b, then n also divides b minus a, and vice versa. If n divides b minus a, then n divides a minus b as well. So these two are equivalent, and in this case we have that b is congruent a mod n, so we see that this and this are equivalent to each other. Okay, so saying a is congruent b mod n is the same as saying b is congruent a mod n, and in either case n divides a minus b, or equivalently n divides b minus a. Okay, so that observation we have recorded over here. And let's see an example. So suppose n is equal to 12, so that's a natural number. Then 16 is congruent 4 mod 12. Well, what does this mean translated? It means that when I take 16 minus 4, well, I get 12, and 12 certainly divides that. Similarly, minus 1 is congruent 11 mod 12, because minus 1 minus 11 is equal to minus 12, and 12 does divide this. Okay, so that is what this relation is on the set of integers. We say that they are congruent modulo n if n divides the difference of the two integers. So we have just introduced this congruency modulo n, and let us prove this little lemma which enables us to calculate things modulo n. So this lemma says that if n is any natural number and a, b, c and d are integers such that a is congruent b mod n and c is congruent d mod n, then if I add these two, I get a plus c, and if I add these two, I get b plus d. Then a plus c is congruent b plus d mod n, and if I multiply these two, I get ac. If I multiply these two, I get bd, and it turns out that ac is congruent bd mod n. In fact, as a corollary, we also get from here that since we know that these two can be swapped, whenever c is congruent d mod n, we also know that d is congruent c mod n. So if we apply this result now to these two, I can add these two, and that's congruent the sum of these two mod n. So I also get a plus d is congruent b plus c mod n. And if I multiply these two, that's congruent the product of these two mod n. And so you also have that AD is congruent BC mod n. But all this just arises once we have proved this thing. So let's prove this. What we know is A is congruent B mod n. Well, translated, it just means that n divides the difference of these two. So n divides A minus B. Similarly, C is congruent D mod n, and translated, that just means that n divides C minus D. So we also have this. Now n divides this integer and n divides this integer, so n also divides their sum. So n divides a minus b plus c minus d, and we can rearrange this to read a plus c minus b plus d. So you have this thing, and that's the same as saying that a plus c is congruent b plus d mod n. After all, what does this mean? It means that n divides this minus this, which is exactly this, right? And so we have got this. And now let us also show that AC is congruent BD mod n. Okay, so let us look at AC minus BD, and we want to show that n divides this. Now all we know is that n divides a minus b and n divides c minus d. So how can we conclude that n divides this? Now, well, let us try to get the term a minus b somehow over here. So to get that, I will subtract bc and add bc, because then in these first two terms c can be taken as a common factor, and then you are left with a minus b just as over here. And likewise here, then b turns out to be a common factor, and then what I'm left with is c minus d, about which I know something. So indeed, if I add and subtract bc over here, then taking c as a common factor I get a minus b, taking b as a common factor I get c minus d. Now I know something about these two, namely that n divides this and n divides this. So we know that n divides this and n divides this, but then n will also divide any combination of these two integers with integer coefficients, and c and b are indeed integers. So we know that n divides this whole thing, and so n divides this. So we have got that n divides AC minus BD, but that's the same as saying that AC is congruent BD mod n. After all, what does this mean? This means that n divides AC minus BD, and that's exactly what we have shown. So this proves this lemma, and this will be useful in computations involving modular arithmetic. Alright, so we have introduced this relation of congruency mod n on the set of integers. So we say that an integer a is congruent an integer b mod n if n divides a minus b. Now let us show that this relation is in fact an equivalence relation on the set of integers. So we want to show that it is reflexive, symmetric and transitive. Okay, so let's prove this theorem now. So this theorem says that if n is any natural number, then congruency mod n is an equivalence relation on Z. So let's start with reflexivity. Here we have to show that for any integer a is congruent a mod n, but a minus a is 0. So all we have to do is to show that this natural number n divides 0, but that's of course true because 0 is equal to n times the integer 0. So this is true, and so a is congruent a mod n. Now let's show symmetry. So this says that whenever a is congruent b mod n, then b is congruent a mod n. But this was our observation that we had made 2 slides back. But let's give a detailed proof. We have that a is congruent b mod n. That just means that n divides a minus b. In other words, n times some integer is a minus b. But if I multiply throughout by minus 1, I get minus of a minus b is minus q times n. And this is just b minus a, and so we have got that b minus a is equal to some integer, namely minus q times n. So n divides b minus a, but that's the same as saying that b is congruent a mod n. So we also have symmetry. And finally, let us show transitivity. So here we have to show that whenever a is congruent b mod n and b is congruent c mod n, then a is congruent c mod n. But what does this mean? A is congruent b mod n, that means that n divides a minus b, and similarly b congruent c mod n means that n divides b minus c. So n divides this integer and n divides this integer. So n will also divide their sum. So n divides a minus b plus b minus c, and this minus b cancels against this plus b, leaving a minus c. So we have got that n divides a minus c, but that's the same as saying that a is congruent c mod n. So we have also got transitivity. So since the relation is reflexive, symmetric and transitive, it follows that it's an equivalence relation. We introduced this relation of congruency modulo n on the set of integers, and we have just seen that this is an equivalence relation. Now Zn, Z subscript n, is going to be the set of all equivalence classes for the equivalence relation of congruency modulo n. So we would like to know something more about these equivalence classes, and this theorem tells us how many distinct equivalence classes there are. So this theorem says that if n is any natural number, then there are exactly n distinct equivalence classes for this equivalence relation of congruency modulo n, and these n distinct equivalence classes are given as follows: the equivalence class containing 0, the equivalence class containing the integer 1, equivalence class of 2, and all the way up till equivalence class of n minus 1. So all of these equivalence classes are distinct, and these are the only ones which are possible as equivalence classes for this equivalence relation. Okay, so let us first show that these are the only equivalence classes, and then we will also show that they are also distinct. Okay, so here is the proof. We'll first show that these are the only equivalence classes. So if I have any integer a, then let's see what its equivalence class is. Now first of all, any integer can be divided by this n, because n is non-zero, it's a positive integer. So by the division algorithm, we know that there exist integers q and r such that a is equal to q times n plus r, and this r is bigger than or equal to 0 and strictly less than this n. So this means that a minus r, if I bring this r to the other side, is equal to q times n. Okay, in other words, n divides a minus r, and that means that a is congruent r mod n. Indeed, what does this mean? This means that n divides a minus r. Now since this r is an integer which is related to a under this congruency modulo n, it means that they have the same equivalence class. So the equivalence class containing a is the same as the equivalence class containing r. But this equivalence class containing r is one of these equivalence classes, because we know that r is strictly less than n and bigger than or equal to 0. So r is either 0 or 1 or 2 all the way up till n minus 1. Okay, so this r is one of these integers 0, 1 up till n minus 1, and so the equivalence class containing r belongs to the set of equivalence classes of 0, of 1 and all the way up till of n minus 1. Okay, and so we have got that for any integer, the equivalence class containing that integer has to be one of these. So these are the only possible equivalence classes. Now let us show that these are also distinct. So let us suppose that there are two equivalence classes amongst these which are the same. So you have that the equivalence class of r is the equivalence class of r prime, where r and r prime are two different numbers in between 0 and n minus 1. So one of them will be bigger. Let's suppose that r prime is strictly bigger than r. Now since these two equivalence classes are the same, that means that this r which belongs to this one also belongs to this, and so they are related. So that means that r is congruent r prime mod n, or equivalently r prime is congruent r mod n. So what does this mean? This means that n divides r prime minus r. N divides r prime minus r. So that means that there exists an integer q such that n times this integer is equal to r minus r prime. Now note that since r prime is strictly bigger than r, this is a positive integer, and we know also that n, being a natural number, is also positive. So it has got to be the case that since the product of these two numbers is positive, either both of them are negative or both of them are positive, but we know that n is already positive, so q has got to be positive. So that means that q is a natural number. Okay, so that means that q is bigger than or equal to 1. So if I multiply both sides of this inequality by n, which is a positive number, the inequality is preserved. So since q is bigger than or equal to 1, it follows that n times 1 is less than or equal to n times q. But n times 1 is n, and n times q we know is equal to r prime minus r. Now r prime is at most n minus 1, and r is bigger than or equal to 0, so minus r is less than or equal to 0. So r prime minus r is less than or equal to n minus 1 minus 0, right? And so we have at the end of the day got that n is less than or equal to n minus 1. Okay. Now if I add minus n to both sides, then I get 0 is less than or equal to minus 1, and if I add 1 to both sides, then we get that 1 is less than or equal to 0. But some time back we had shown that 1 is strictly bigger than 0, and by the trichotomy law that violates this. So we have got a contradiction, and this contradiction shows that our original assumption that two of these equivalence classes are the same, which correspond to different numbers in between 0 and n minus 1, is false, and so these are all distinct. So we have shown that these are the only equivalence classes, and moreover they are all distinct. Okay, so that proves this theorem. Okay, so let's see a concrete example. Let's take the natural number n equal to 2. So the relation that we are looking at is congruency modulo 2, and then we are going to see what the equivalence classes are. So there will be two equivalence classes since n is equal to 2, and these are the equivalence classes, namely the equivalence class containing 0 and the equivalence class containing 1, because n minus 1 when n is equal to 2 is equal to 1. So let's see what these two equivalence classes are. So we know that these are the only equivalence classes, and moreover they should be distinct. So let's see all that. So what's the equivalence class containing 0? Well, it's a set. Set of what? Of all those integers which are related to 0 under the relation of congruency modulo 2. So in other words, it's the set of all integers a such that a is congruent 0 mod 2. What does that mean? That's the set of all integers a such that 2 divides a minus 0. And what does it mean to say that 2 divides a? It means that a is equal to 2 times some integer. So there exists an integer m such that a is equal to 2 times m. So this equivalence class is the collection of all those integers a such that a can be written as 2m for some integer m. In other words, it's the collection of all 2m's where m is any integer. But this we recognize is the set of even integers, and so this equivalence class is simply the set of all even integers, which is the set containing 0, 2, 4, 6 on the one hand and minus 2, minus 4, minus 6 and so on the other hand. So that's this equivalence class. Now let's look at the other possible equivalence class, which is this equivalence class containing 1. Well, what is that? Again, it's a set. Set of what? Set of all those integers which are related to this 1 under the relation of congruency mod 2. So it's the set of all those integers a such that a is congruent 1 mod 2. Well, what does that mean? That means that 2 divides a minus 1. And what does this mean? It means that a minus 1 is 2 times some integer m. So if I rearrange this, this is the same as saying that a is equal to 2m plus 1 for some integer m. In other words, this set is the set of all 2m plus 1's where m is any integer. And this we recognize is a set of all odd integers, which is the set containing 1, 3, 5 on the one hand and minus 1, minus 3, minus 5 on the other hand. Okay, so indeed we see that these two are distinct. On the one hand we get even integers, on the other hand we get odd integers. And by the theorem that we just proved, we know that under the relation of congruency mod 2, there are only two possible equivalence classes, namely these two. Okay, so the set Z2, Z subscript 2, will be this set containing these two equivalence classes. So in the previous example, we saw a concrete example of what happens to the equivalence classes when n was 2. But now here is the general theorem which describes equivalence classes. So this theorem says that if n is any natural number and a is an integer, then the equivalence class containing a is this set. It's the set of all a plus m times n, where m is any integer. So in the previous case, when n was equal to 2, there were two equivalence classes, namely equivalence class containing 0, in which case you would get that equivalence class to be the set containing 0 plus 2m, and that was the set of all 2m's where m was any integer, and this was the set of even integers. And when you look at the equivalence class containing 1, you got 1 plus 2m, and that was the set of all odd integers. But this is the more general result for arbitrary n's. So we want to show that this set is the same as this set. So we have the equality of two sets. So we'll show that this set is contained in this set and vice versa, this set is contained in this set. So let's start with the fact that this equivalence class is contained in this set. So let's take any element b in this equivalence class. What does it mean? That means that this b is related to a under the relation of congruency modulo n. So we know that b is congruent a mod n, which just means that n divides b minus a. And what does that mean? That means that there is some integer m0 such that when multiplied by n you get b minus a. So b minus a is equal to m0n for some integer m0. If I rearrange this, I get b is equal to a plus m0n, right? And this is exactly in this form. It is a plus some integer times n. So this b does belong to this set. So anything in here on this left hand side actually belongs to the right hand side set. So this left hand side set is contained in this right hand side set. Now let us show that this right hand side set is contained in this left hand side set. So we start with an element b in this set. So that means that this b can be written in this form for some integer m0. But that means that b minus a, if I bring this a to this side, b minus a is equal to m0n. but that means that n times some integer is b minus a, so n divides b minus a, which is the same as saying that b is congruent a mod n. After all, this just means that n divides b minus a, which we have. But b is then related to a under this equivalence relation of congruency modulo n, and so b belongs to the equivalence class containing a. And so we have got that this right hand side set is also contained in this left hand side set. So these two sets are the same. So let us see what we have just learned. Let n be a natural number and a be any integer. Then we know that the equivalence class containing a by definition is the set of all those integers b which are related to a. So b is congruent a mod n. And the previous result has given a description of this set. It's the set of all a plus mn where m is any integer. And what does this set look like? Well, when m is equal to 0, you have a. When m is equal to 1, you get a plus n. When m is equal to 2, a plus 2n. When m is 3, a plus 3n, and so on. And if m is minus 1, you have a minus n. M is minus 2, a minus 2n. M is minus 3, a minus 3n, and so on. So this is what this equivalence class looks like. So let's see some further examples. If n is equal to 1, well, that's a natural number. And by a result that we have just seen, we know that there is only one equivalence class under the relation of congruency modulo 1. And we also know what the description of this equivalence class is. Well, a is equal to 0 and n is equal to 1. So it's the collection of all 0 plus m times 1 where m is any integer. So it's the collection of all integers. So this equivalence class is just the set of all integers. Now let's take n is equal to 12. In that case, we know that there are 12 different equivalence classes, and they are given by the equivalence class containing 0, equivalence class containing 1, all the way up till equivalence class containing 12 minus 1, which is 11. So these are the 12 distinct equivalence classes. Okay, so let's look at the equivalence class containing 6. That's the equivalence class which is given by 6, because a is equal to 6 plus m times n, which is equal to 12, where m is an integer. So it's the set of all 6 plus 12m where m is an integer. So what are some of the members over here? So if m is equal to 0, we have 6, and then when m is equal to 1, 6 plus 12 is 18. When m is equal to 2, then 6 plus 24, which is 30 on the one hand, and if m is equal to minus 1, then 6 minus 12 is minus 6, and so on. So it's this set. And then all of these are related to 6 modulo 12, and so the corresponding equivalence classes will be the same. So we know that the equivalence class containing 6 is the same as the equivalence class containing 18, is the same as the equivalence class containing 30, is the same as the equivalence class containing minus 6, and so on. Okay, and so finally we will give the definition of what this set Zn is. So if n is a fixed natural number, then Zn is simply the set of all equivalence classes under the equivalence relation of congruency modulo n. Okay, and this set of these equivalence classes is called the set of integers modulo n. Okay, so this Zn has just n elements. Okay, so let's see some examples. If n is equal to 1, then we saw that under the equivalence relation of congruency modulo 1, there is just one equivalence class, and in the previous slide we saw that this equivalence class is actually the set of all integers. Okay, so this Z1, which is the set of all the equivalence classes, well, there is just one equivalence class, and that equivalence class we have seen is the set Z. So this Z1 is a singleton set whose only element is itself a set, namely the set of integers. Now let's look at Z2. So then the relation is congruency modulo 2, and now there are two equivalence classes, the equivalence class containing 0 and the equivalence class containing 1, and Z2, the set of integers modulo 2, is the set containing these two equivalence classes. Now we had seen that this equivalence class containing 0 is the set of even integers, and the equivalence class containing 1 is the set of odd integers. So this Z2 is a set containing two elements, and these two elements are themselves sets. One is the set of even integers and one is the set of odd integers. Okay, so this is the set of integers modulo 2. Now let's look at the set of integers modulo 3. Now there will be three different equivalence classes: the equivalence class containing 0, equivalence class containing 1, and equivalence class containing 2. And if we take n is equal to 12, then the set of integers modulo 12 is this set Z12 comprising these 12 equivalence classes. Okay, so what are we going to do next? Now, so far we have a set, the set of integers modulo n. We are going to develop an arithmetic of these. So we are going to define addition modulo n. So this will be a map which takes two integers modulo n and produces a new integer modulo n. And we'll also see multiplication modulo n. So that takes two integers modulo n and produces a new integer modulo n. And we will see the properties of these. So we'll see that the usual familiar properties of arithmetic hold. So addition is commutative, associative. There exists a zero element. For every element there is an additive inverse. Then multiplication is commutative, associative. There exists a multiplicative identity. But multiplicative inverses of non-zero elements are not guaranteed to always exist. Okay, and we will also see that the distributivity law holds. So actually this forms a ring, a commutative ring in general. Okay, so we don't have to know what a ring is, but the usual properties hold, except that multiplicative inverses may fail to exist. But we will also see that if this p, the natural number, happens to be a prime number, then in fact multiplicative inverses for non-zero elements also exist, and so this forms a field. Okay, so we will see all these things next time.